Hey guys, this is a review for Spiral 18. We're going to start off with looking at some properties of logarithms. For each of these, I'm going to either expand or condense, and I'm going to go through these in order to build some problems here. Okay. First thing I might do for number 1 is take this 4 and distribute to each piece of this. So I'd rewrite this as log base 8 of 7 to the 4th times 5 to the 4th times 12 to the 20th, and because all those are really large numbers, I'm going to leave those as is. Okay, and then I'm going to break this up. If I'm multiplying on the inside, that means I'm adding on the outside. Log base 8 of 7 to the 4th plus log base 8 of 5 to the 4th plus log base 8 of 12 to the 20th. Alright, next step is I'm going to take each of these powers and bring them down front, and then I'll be done. For expanding, I generally try to clean stuff up, and then I'll break things up based on adding or subtracting, and then I will deal with powers. So we get 4 log base 8 of 7 plus 4 log base 8 of 5 plus 20 log base 8 of 12, and at this point we are done. For number 3, in a similar fashion, we're going to expand this. And the first thing I might do is clean this up, and by that I'm going to turn my cube root into a 1/3 power. So we get log base 3 of y z to the 6th, x to the 1/3. Okay, I'm going to break this up based on addition because we're all multiplication on the inside. So log base 3 of y plus log base 3 of z to the 6th plus log base 3 of x to the 1/3, and now bring any powers out in front. Log base 3 of y plus 6 log base 3 of z plus 1/3 log base 3 of x. For number 5, I'm going to be doing some condensing. And in the opposite order, I'm going to do some powers first, and then I'll combine things in terms of adding and subtracting. So I'm going to take each of the numbers out front and convert them to powers. That gets me log base 5 of 2 to the 25 minus log base 5 of 11 to the 5 minus log base 5 of 7 to the 5th power. Okay, for ones with both positives and negatives, I tend to build a log, and this log base 5 with a nice fraction on the inside. Positive stuff goes on top, so that's going to be 2 to the 25th. Negative stuff goes on the bottom, so that's going to be 11 to the 5th, 7 to the 5th. And at this point, I am done. For number 7, we're going to be combining again. And again, first thing we'll look for are powers, nothing, nothing, nothing. And here we're dividing by 2, so I'm going to rewrite that as a 1/2 power. So log base 5 of y plus log base 5 of z plus log base 5 of w plus log base 5 of x to the 1/2. And here's somewhere that I keep seeing this get converted to just squared, which you can't do. A half and 2 are two different numbers. You could rewrite this as a square root. I'm going to do that in the next step. Or you could leave it as a 1/2 power, and that would be okay. Everything here is positive, so I don't really need a fraction this time, because on the inside all that's going to happen is these are going to get multiplied together. So y times z times w times x to the 1/2, or the square root of x. Next up, we got some log equations. I'm going to start off with number 9. And my first goal is going to be to get this piece by itself and then convert to logs. To do that, I might do minus 4 to both sides and then divide the whole thing by 4 afterwards. Minus 4 is going to be 88, divided by 4 is going to be 22. So I'm going to rewrite this as 3 to the 5n plus 7 is equal to 22. Now I'm going to convert this to a log. It's going to be log base 3 of 22 is equal to 5n plus 7. Now I've got to get n by itself. Okay, minus 7 to both sides. Got log base 3 of 22 minus 7 is equal to 5n. And then finally, log base 3 of 22 minus 7 over 5 is equal to n. I'm just going to clear that up to make sure we can see that's a 5. For number 11, I've got to do the same thing, get this log part by itself, and then we're going to convert this to an exponential so that we can see what's going on here. Here we only really have one step. I've got negative log of something equals negative 1. I could write this as log of that something equals positive 1. So that means that 5 to the 1 is equal to 10p. In other words, 5 is 10p. If I divide by 10, 5/10 or 1/2 is equal to p. And if I plug that in, just to check, 10 times 1/2 is 5. Log base 5 of 5 is 1. Negative 1 is negative 1. That works. For number 13, I've got a log on both sides. That means that if the base in this is the same, okay. I've got nothing else in the problem, check. The insides have to be equal. So negative 2x is equal to 8. That means that x is equal to negative 4. And if I plug that back in, negative 2 times negative 4 is positive 8. I get log base 9 of 8 equals log base 9 of 8. Check for the win. Number 15, we're going to do some log combining first. I've got two logs on the same side. I can combine those two using the properties of logs. Because it's plus, I can multiply the inside. So that's log base 10 of 2 times x plus 1 is equal to 1. Okay, I'm going to put that base 10 in just so I can see that, okay, now I can convert this to an exponential. 10 to the 1 is equal to 2 times the quantity x plus 1. In other words, 10 is equal to 2x plus 2. X equals 4. If I plug this back in, to here we get 4 plus 5. 2 times 4 plus 1 is 5. 2 times 5 is 10. Log base 10 is 1. And that's the last problem on this side. Let's go up the other side. Same thing over here. We're having two logs on one side, so what I'm going to do is combine those with log properties. Plus means multiplication. So we get log base 6 of x times x plus 1 equals log base 6 of 12. Since both sides are now just in terms of log base 6, I'm going to write this as x squared plus x is equal to 12. I'm going to bring everything onto one side and factor. X squared plus x minus 12 is equal to 0. That means x plus 4 times x minus 3 is equal to 0. And from this, x equals negative 4, and x equals 3, positive 3. When I go and plug these in, negative 4 immediately gives me something that does not work, because log base 6 of negative 4 is an undefined answer. Put log base 6 of 3 and log base 6 of 4 combine to get log base 6 of 12. So in this case, x equals negative 4 would be extraneous, because even if I plug it in, it doesn't work. X equals positive 3 works. Number 14 rather. If I've got logs on both sides, same base, nothing else, that means that the insides have to be equal. So x plus 8 is equal to 1. That means that x is equal to negative 7. When I plug that in, I get log base 3 of 1 is equal to log base 3 of 1. We are golden. For number 12, we are looking at a log equation. I'm going to get the log by itself. There's only 1 in here. Then I'm going to convert to exponential. Start by dividing both sides by negative 10. And I get log base 12 of v minus 6 is equal to 1. Convert to exponential. 12 to the 1 is equal to v minus 6. v is equal to 18. If I plug that back in, we get v minus 6, so 18 minus 6 is 12. Log base 12 of 12 is 1. Negative 10 times 1 is negative 10. On the other side, we got to get my exponential stuff by itself, and then we're going to convert to a log. So we're going to start by adding 9 to both sides. And I get negative 8 times 12 to the 7 minus 6x is equal to 28. Divide both sides by negative 8. And we get 12 to the 7 minus 6x is equal to, and this is totally not 28, this would have been negative 10. Negative 10 over negative 8 is going to be 5 over 4. That actually is much nicer because now we get an answer that will work. I'm going to convert this to a logarithm, so it's going to be log base 12 of 5 over 4 is equal to 7 minus 6x. I'm going to subtract 7 from both sides and divide by negative 6 to get an answer of log base 12 of 5 over 4 minus 7, and then divide that whole thing by negative 6 is equal to x. Next up, we got some log graphing. In this case, we're going to look at graphing the exponential first, and then only graph the log part of that. That's the strategy we've been using for this, and we're going to keep it up. We're going to start by making an exponential equation for this. So I've got to turn this into an exponential. That's going to be, so we're looking at this exponential function, and in doing so, I'm going to start by converting this into x equals log base 2 of y minus 3 minus 5. And now I'm going to solve for y. But before that, I'm going to ask if anybody would like to say hi. Would anybody like to say hi?
Hi.
Wow, the after-school crowd is very excited to see you guys, too.
Absolutely. Hope you're all doing well.
It's going to be really fun when he realizes that he's talking to himself
Oh, man.
when he looks at this video tomorrow. So now let's try and solve for y. I might add 5 to both sides first. And we get x plus 5 is equal to log base 2 of y minus 3. Convert to exponential. 2 to the x plus 5 is equal to y minus 3. And finally add 3 to both sides. 2 to the x plus 5 is equal, plus 3 is equal to y. Let's make a table and find the asymptote. Asymptote's going to be a plus 3. And my table, I'm going to choose values to make that exponent negative 1, 0, and positive 1. In this case, that's going to end up being negative 6, negative 5, and negative 4. Plugging those in, I get 2 to the negative 1 is going to be a half plus 3 is 3.5. Negative 5 is going to be 2 to the 0 is going to be 1 plus 3 is 4. And negative 4, we get positive 1. 2 plus 3 is 5. With an asymptote at y equals 3. Remember, we're not actually graphing this. This is our exponential function. We're going to use this to make a log function. Many of you lost points on this section on the last spiral, because instead of graphing a log function, you graphed the exponential function. So to get that log function, we're going to switch our x and y's. We get 3.5, negative 6. We're going to get 4, negative 5, and we're going to get 5, negative 4, with our asymptote at x equals 3 instead of y equals 3. I'm going to graph that guy first, a nice vertical asymptote, and then we're going to go at 5, negative 4. We're going to go at 4, negative 5, and 3.5, negative 6 to get a log graph that looks something like this. The domain would be x is greater than or equal to 3, and the range would be all real numbers. Just like for the exponential version, the range would be x is greater than or equal to 3, and the domain would be all real numbers. Going to skip 18, skip 19, and bounce over to number 20. Same thing, I've got to make an exponential function, and that's going to look something like this. 5 to the x minus 5, and then minus 3 is equal to y. I'm going to build my table. And again, this is just used to make a log table. I'm going to use the points positive 4, positive 5, and positive 6. When I plug these values in, 5 to the negative 1 is positive a fifth. Minus 3 is negative 2.8. We're going to have 5 to the 0 is 1, minus 2 is negative 2, minus 3 is negative 2. And 5 to the 1 is 5, minus 3 is going to be positive 2. Finally, we have a horizontal asymptote at y equals negative 3. Going to my log equation, and again, we are graphing the log equation, not the exponential. Many of you lost points because you graphed an exponential function instead of the log part. We're going to switch our x and y, so negative 2.8 and 4, negative 2 and 5, and 2 and 6. And our new asymptote is going to be x equals negative 3 instead of y equals negative 3. Draw that in. We're going to have 2, 6. We're going to have negative 2, 5. And we're going to have negative 2.8 and 4. This would look something like this. And finally, now we are in matrix land, which is super exciting. I'm going to do some of these problems. I am not doing all of these problems. I'll probably choose one out of each 4 to do. Maybe I'll do 2 multiplication ones to give you guys some extra examples, but for the most part, these are relatively straightforward. That being said, I might as well do one of the easy ones, so I'll choose number 23. That's going to be negative 4q, and that's multiplied by the matrix 0 minus m minus 3, m plus 3. So that would be negative m minus 3. Negative 4mq minus 4, I'm going to zoom in so I can actually fit this in my parentheses, minus 4p squared would be negative 4mq minus 4p squared. And then 0 minus 3m minus 1 would be minus 3m plus 1. When I multiply negative 4q by each of these things, this is scalar multiplication, we get positive 4mq plus 12q. We get positive 16mq squared plus 16qp squared. And then finally 12mq minus 4q. This is my final answer. Let's see which other one looks good. I don't know. I kind of like the idea of 25, so let's do that one. Okay, this is matrix multiplication. We're going to multiply first row, first column. 5 times 4 is 20. 3 times 6 is 18. Negative 6 times negative 6 is 36. Add those up, and what do we get? 6874. Next, we're going to do row 1, column 1, or column 2. We get 5 times 2 is 10. 3 times 1 is 3. Negative 6 times negative 3 is 18. Altogether, we get 31. Next up, we're looking at row 2, column 1. 4 times 6 is 24. I'm going to be annoyed about this, I think, because I wrote that in the wrong place. Plus 30, and then plus 6, which is going to be 60. And then finally, we've got row 2, column 2. So that's going to be 6 times 2 is 12. 5 times 1 is 1. Negative 1 times negative 3 is going to be 3. 17, 20. My final matrix would be 74, 31, 60, and 20. Looking at 27, this is multiplication again, so row 1, column 1, and immediately I see those don't actually match up. I can't multiply one element by 2. This one is undefined. Is that a cop-out for me to choose that one to do so I do less work? Yes. Am I feeling sorry about it? No. Number 29. We've got to solve this matrix equation. And to do that, we're going to subtract my left matrix to both sides. So if negative 3b is equal to negative 3, negative 3, negative 18, and negative 12. When I multiply both sides by negative a third, we end up with 1162. That's my final answer for B.